So what I want to do, I want to tie that into what we talked about yesterday, or last time. Remember this drawing? We have these conductive rails, and so it forms three sides of a circuit, and we have a conductive rod that's pressed up against those rails, and we slide it back and forth. Why do we do that? So we can change the area of our circuit very easily, right? And we used Faraday's law yesterday, last time. We used Faraday's law, and what did we come up with? We used that to figure out what the EMF generated by this changing flux. We said the EMF generated, let's just use magnitudes for now. The magnitude of the EMF generated was the change in flux over a change in time, right? And we use that, and then we could replace this with just a resistor and a battery equal to that EMF, and we used Lenz's law to figure out what direction to put the battery. Remember that? What direction did we put the battery? What direction does the current flow? Oh, sorry. This is moving to the right. You have to know which direction it's moving, don't you? We moved that yesterday, or it wasn't yesterday, 2 days ago. This was moving to the right, so I'm trying to replicate what we did 2 days ago. It was moving to the right. The area is getting bigger, which means there's more and more flux into the board. So a current has to get set up to try to subtract from that, try to get it back to a lower flux. So it's going to go counterclockwise. So the current that's induced goes counterclockwise. So that's the same as a battery with that orientation, right? Positive up with the EMF equal to d flux dt, or delta flux delta t. And we figured that out the other day. But there's another way we could look at this. We could say that this conductive rod moving in a magnetic field, the charges move, right, because they feel forces. Charges moving in a magnetic field feel forces and move. And we just figured out that it generates an EMF across the rod, right? This motional EMF across the rod equal to BVL. And what did we get the other day when we used Faraday's law for this exact same case? We got BVL for the EMF generated in this loop by the change in flux. So two different ways of looking at the same problem, and they give us the same result, right? You can look at this a number of different ways and get the same result. That's the point I'm trying to make here. All right? Okay, let's do this. Loop of wire. Take your magnet. Drop the magnet towards the loop of wire. What happens as it approaches the loop of wire from above? Let's fill in the dot and cross here. Show me which direction is the current that's induced in that loop of wire. This falling magnet has a magnetic field out here, right? As it gets closer and closer to the ring, the magnetic field gets stronger and stronger. You see that? If it's far away, the magnetic field's weak from that magnet. As it gets closer and closer, it gets stronger and stronger. So there's an increasing magnetic flux in the downward direction through that loop. So that means that the current has to get set up to create its own magnetic flux up to counteract that change. The magnetic flux is down and increasing, so it creates its own magnetic flux that's up to counteract the change from the magnet. So that means that loop of wire, I could replace that loop of wire with a magnet, right? With its north pole pointing up. So what happens? What's the interaction between these two? They repel each other. You okay with that?